In this example, we'll look at computing the contribution of vibrational modes to the specific heat, constant volume. And in the example, stick with nitrogen gas because I won't have to look up new parameters for it. But find the vibrational contribution to the molar specific heat of N2 gas at 1,000 Kelvin. So it's nitrogen gas at 1,000 Kelvin. And I looked up the vibrational since they want the vibrational, and I found that the characteristic vibrational temperature was 3374 Kelvin, same as in the previous problems. Now they just want to calculate the molar specific heat, and so we computed that in one of the previous segments to be R theta vibration over T squared times this factor here. And it's just a matter of plugging in all the appropriate values. The temperature is 1,000, so that ratio theta vibration over temperature is the same in all of these. And then, of course, the ideal gas constant. I used it in the 8.31 joules per Kelvin mole, per mole Kelvin. You may have used calories here, but I generally stick with the metric on most situations. The computation then boils down to this, and when I did it, I got 3.47 joules per mole Kelvin for the specific heat. Just the vibrational, this is specific heat at constant volume, and it's just the vibrational contribution to that. And I actually looked up an experimental value, and the experimental value was 3.43 joules per mole Kelvin. So I would say reasonably pretty well, really very good agreement, I would say, on this. That gives you some idea of the accuracy of this formula, at least for relatively high temperatures in this case.